Good? Okay.
We probably don't need the mathematical derivation for this time, right?
What?
We probably don't want the mathematical derivation, just like the concept.
No, yeah, I'll just go quick.
Yeah.
So essentially, basically, we have a neural net. Okay. And the classic example that everyone starts with is digit recognition. So you have a picture of a 1, say, and you feed that into the network, and it has 10 output nodes, and you want to train the network to, when you show it a 1, it makes the first one light up. When you show it a 2, it makes the second one light up. When you show it a 3, it makes the, and so on. Okay, so you want it to classify the digit you show it. Okay? And so this network, basically the way each one calculates its own activation uses these weights. So each one of these lines has an associated weight, which is basically how strong it is. A weight is just a number.
Is it like kind of like the probability that you would transition from one state to another?
It's not really a probability. It's like how strong, it's essentially like in the brain, you can have two neurons that are like have a connection between them, and it's basically representing that.
It's like, how important should it be? Does it deserve to go to the next layer that much or not?
Yeah, exactly. Where's the eraser? Okay. And so these weights are basically just numbers, and we can tune them around and change them, and there's a lot of them, right? So there's going to be one for every connection. And so the goal now is to adjust the weights and change them bit by bit until the network does what we want it to do. Okay? Make sense? And we have to have some way of telling the network when it does good and when it does bad. So usually we have some function that we usually call cost, or sometimes it's called loss, which basically says, how good did the network do? All right? And now I'm going to draw a graph, and the y-axis is going to be loss. So basically, if the network's doing good, that means this is going to be low. Loss or cost is going to be low. And the network's doing bad, cost is going to be high. Okay? Yep. And on this axis, I'll put one of our weights. Okay, so this is just one of those connections, one of those numbers that we can tune and change. And basically, as we tune and change it, the loss is going to change as well. Right? And so what we want to do is we want to change this weight until we find basically the lowest or close to the lowest point of loss or cost. And that will make our network better. If our network is doing bad right now and then we change this weight to down here, that means our network just did better, right? But if our weight starts up here, we can't really see this graph, really. I've drawn it so we can see it, but from the point of view of the network, it can't see the graph. But what it can see is where the weight is, and also using math, we can calculate the derivative of the weight with respect to loss.
Loss with respect to the weight?
Yeah, sorry. The derivative of loss with respect to weight, which will tell us this slope, and that is tangent, definitely. And you guys have both taken calculus, right?
Yeah.
So derivatives should be familiar to you. They just tell us the slope of the function at a given point, right? And essentially, you'll notice if the derivative is negative, that means that if we increase our weight a little bit, that's going to decrease our cost a little bit. And conversely, if our slope is positive, that means if we decrease our weight a little bit, we're going to decrease our loss again, right? So basically, what we can do is we can take our weight, find the slope, the derivative, and then if it's negative, add a little bit. If it's positive, subtract a little bit, and then do that again. So find the next slope, and then keep doing that, and hopefully you'll land down in this valley. So does that make sense so far?
Yeah.
Okay. And one more thing I'll add is that you'll notice that not only does negative slope mean you have to increase it, and positive slope means you have to decrease it, the magnitude of the slope is important too. So if you're up here, you have a really steep slope, and if you're closer to the local minima, you have a smaller slope, a less steep slope. There's no real word for less steep in English, which is kind of annoying. Shallower, maybe. Shallower slope. So essentially what we do, so a very steep slope means you have to go a really long ways to get to this local minimum, and a really shallow slope means you don't have to go as far to get to the local minimum. So we should basically also be taking steps in proportion to the magnitude of the derivative. Does that make sense? Yeah? Okay. So essentially our new weight is going to be our old weight minus the derivative of our old weight with respect to loss. So we'll write that this way. And usually we also multiply this by some constant, which is called the learning rate. And essentially this is just something that we can play around with to get the network to learn well and not. Basically, if it's too big, it becomes very unstable. So, but essentially, this is how the networks learn. And you're also doing this not only for one weight, but you're doing it for all the weights at once. So you take a step like this for every weight at once, and then you recalculate the derivative for all the weights, and then you take another step, and you just do that, and eventually you get to one of these valleys. So does that all make sense?
Yeah.
Andre, Jaeger, you got anything to add?
Then the multivariable of all the weights would just be the gradient, right?
Yeah, okay, so basically the derivative of a lot of things at once is called the gradient, and you are descending this graph. So together this is called gradient descent. That's where the name comes from, this technique. And it's also called backpropagation because when you calculate derivatives, you have to do it backwards through the network, which is just like a quirk of calculus, essentially, of how the calculus works out. So that's why it's called backpropagation.
Yeah, and then also to escape those local values sometimes, we want to use stochastic gradient descent or other methods to try to...
So really, if you get stuck in one of these, there's no reliable way to solve it. But it's fine because usually you get to a good enough place and you call it a day.
It's kind of best in check. Like there are a lot of different methods. There are a lot of fancy learning rate schedulers. So the idea is that you change the learning rate over time. So for instance, one idea is you have a really big learning rate when you start out. As you can see, according to that equation, that means that given a derivative, you amplify it a lot. So like you take bigger steps. But then as time goes on, your learning rate becomes really small, so you become more conservative with how far you go. That's one way to explore the space and then begin to exploit known minima.
techniques to like get that to work better as there are Pokemon. Kind of like, I don't know, there's probably 3,000. Actually,
I think
there's probably bigger Pokemon.
No, I think there's less than, I think it's like 800.
Really? Either way, it's probably from Pokemon, but even so, it's like similar order of magnitude. of
Yeah,
process.
there's a lot.
Like, yeah, like another example of something that can be done is, I mean, if you imagine, it's kind of like we're rolling down a hill, right? But if we take that analogy a little further, like when a ball rolls down a hill, it has momentum. So how do we just give this momentum? And that's a very real technique that's used. It works in some cases, doesn't work in others.
Yeah.
Is Adam related to this, or is it for different?
Atom is basically an implementation of this, but with some fancy bells
There's
and
memory.
whistles.
Memory. Which helps with like, this is kind of like where am I now? But when you have memory, you can better, understand this. Everyone uses that most of the time.
Yeah.
Another thing to know with this is that you didn't really go through the details of exactly how this gradient is computed here, or like how, like the very, very fine grained details of how we get this, the number that is the derivative. But like in real use, we don't really care because as long as it is differentiable, we know that somebody somewhere has figured out how to get the derivative. And as long as we just apply the chain rule on a series of like mathematical functions, we'll eventually get the derivative somehow.
If you guys want to actually go through the derivation, there's a guy called Varun who presented at a journal club. It's on the website. I sent you a link. But essentially he has this 2-hour thing where he presented and went over all the math. Like it looks kind of complicated, but actually when you see him explain it, it'll make sense. If you're interested in that.
There's also a,
It's on the
I
Facebook
think
website.
Triple One Round goes over.
Yeah.
Yeah, those are cute.